Today we continue our look at the call stack. In this lecture I want you to get an idea of what the call stack would look like and how and when to use it. So let's have a look at some code. When we create a stack frame, and that's what we're doing here in line 2, when we add -12 to the stack pointer, that's creating room for 3 words because we're creating the space of 12 bytes, which is 3 words. But when we do this, we should make sure that creation and destruction matches up. So at the top here we're creating a stack frame, and then down at the bottom here we release that stack space, we destroy the stack frame. And that's because we don't want to just hog all of this room. We'll eventually run out of space if we don't release the stack pointer and release the stack frames that we've used for our subroutines. So when we create a stack frame, we should also undo that at the end, and it should match up perfectly. So what we're also using the stack frame for here is storing some reserved registers. So we store word RA at the stack pointer, so that's keeping a return address for later on. And then we store the reserved register S0, or the saved register S0 and S1 at the stack pointer. Now that's because they are preserved, so the responsibility is on the subroutine to either save the values and restore the values, or not use those registers. So when we save those registers to the stack, that means we could then use them in the subroutine. So after this, you can see it says save unpreserved register S0 and S1. So we're using them in the subroutine. So the subroutine uses these registers that it really shouldn't be using, but because of the stack, we can get away with that by saving the values. And then later on, down at the bottom here, you can see we're restoring those values by taking them off of the stack, or moving them from the stack back to where they were beforehand. So with this technique, you could imagine actually using every register with the stack with subroutines, because you can store all of those values to the stack. It just means that you need to do a little bit of prep work by preparing the stack frame and moving and then restoring values. So let's have a look at this example in practice. So when we start off, the stack pointer is just pointing to this place in memory, so we've got some memory locations down at the bottom of the screen here. You'll notice that these are all incrementing in size of 4, so these are all storing words. But when we call the subroutine, the stack pointer is just pointing to DO. And then, when we carry out line 2 of this, when we add -12, the stack pointer all of a sudden shifts down to the bottom here at C4, and that's subtracting 12, moving down 3 word spaces, or 12 addresses. Then we store a word at the stack pointer, and that word is the return address. So we have the value from RA that's stored in memory at the stack frame. And next we store the word from S0 at 4 of the stack pointer, so we're going up 4. Remember, because it's going downwards, we need to go back up to get to the space above the RA. So above the RA, we're going to have the value from S0. And similarly, afterwards, we're going to have the value from S1. Then at the end, when we get to add immediate and we've moved all of these values back to their original registers, the stack pointer will go back into the previous memory address that it was at, because we've matched these up perfectly. Now those values will still be in memory, but when it comes time for someone else to use the stack pointer, they wind up overwriting those values if they use those registers. So let's have a look at how this plays into subroutines or functions. So on the left here I have function A, and function A is described as calling function B and function C. And then function C also calls function D, so there's a bit of complexity going on here. So what would happen if we ran this? Well, first we create a stack frame for function A, and then the stack pointer would be incremented to the bottom of that, and we would then call function B. And we need to create a stack frame for that. Once it's done, we'll dissolve that stack frame because function B doesn't, or at least we don't know that it calls anything else, but function B doesn't call any other subroutines, so that stack frame can be destroyed. You'll notice function A is still there, and that's because function A is still working. It hasn't called function C yet, but that's what it'll do next. Now, because function C calls function D, we then would need to create a stack frame for function function D. And so you can see this sort of leveling out of the sort of hierarchy of the things that need to be executed. So function A is at the bottom or the top, but remember it's upside down here. So function A is at the bottom because it's the last one that's going to finish executing. For it to finish executing, all of these other stack frames or functions have to be called and executed. So it's going to be the last one to finish off here, and that's mirrored in the structure of the stack because it goes function A, function C, function D, and we can only pop from the top. So this hierarchy here, what it's really showing you is that function A was the first one called, and it needs these other ones to execute before it can finish executing. So we'd have to pop from the top, and that would mean popping function D. So function D would then be destroyed, the stack frame anyway would be destroyed. And then we'd have to do the same for function C. And then function A is the only one that's left, and when that's finished executing, we destroy that stack frame. So you really do need to remember how to do this. Now, when you write code in Java, you're implicitly always pushing things to the stack. So it's very, very important that you understand this concept, because it won't mean that you can program in Java, but it will mean that you understand your programs in Java better. And you can understand how much memory they're going to take up and what could make them more efficient. So it's quite an interesting concept for you to know. It won't revolutionize your programming experience, but it will seriously deepen your understanding of it. So let's have a look at when we would need or not need a stack frame. Now, a subroutine that calls another subroutine always needs a stack frame, and that's because we need to store the return address, otherwise we'll overwrite it. So you always need a stack frame when your subroutine calls another subroutine. That's a very good rule of thumb. Now, a stack frame is not needed for a subroutine if both of these conditions hold. So if it doesn't call a subroutine itself, that's one way it's known as a leaf. Leaf of a tree is just a value or just a dead end. So a subroutine that doesn't call itself could be referred to as a leaf. Or as well, it doesn't modify any preserved registers. Now you could store preserved registers in unpreserved registers if there is no subroutine being called. So for example, if we didn't need to call a subroutine and we weren't ever going to use T3, T4, but for some reason or other we had to save S0 and S1, we could move the S0 and S1 into T3 and T4 and save them there. However, it might just be simpler for you to put it in the stack, just for the sake of your own conceptual clarity of the stack is a safe place, we're storing it there, and we don't overwrite it. Now that's everything I wanted to go over today. I'm aware this is a tricky topic, so I'll make sure that you can get in touch with me if you have any questions. But as always, that's what you should do. But yeah, next we'll be going on to recursion with stack frames. I hope you found this useful. If you have any questions, please do let me know. Thanks.